idea of pre-computed signaling policies that I haven't talked about, but you can read about. And now I want to say something about comparison with existing methods. In our computational study, which involves a very challenging POMDP problem, we have also applied existing methods. And these are POMCP and DESPOT. These are general POMDP type methods involving long look ahead, but no rollout. Long look ahead with pruning or Monte Carlo tree search. DESPOT, these methods are not well suited for multiple agents. DESPOT gave up at 4 agents, could not solve problems with 4 agents. POMCP was able to solve problems with 4 agents, no more than 4 agents, but it gave results that were worse, often worse than the base policy. MAD-PG is a different type of method based on policy gradient ideas, and it is applied, it applies to multi-agent problems. MAD-PG just could not cope at all with our problem. It was just doing very strange things. We worked very hard to make it work, but it simply would not work and would give you much worse results than the base policy. We contacted the authors of MAD-PG to see what may be going wrong, but in all indications, MAD-PG cannot solve this type of multi-robot repair problems. And not only that, it doesn't do sensible things at all. I'll leave you with that, and you can read the computational results from the paper that's posted on my website. And I welcome your questions. I'm sorry about the taking over.
Thank you so much for that talk. And I think one thing I know, it's always personally frustrating when I don't have enough time to share some of the results I'm excited about. So if you wouldn't mind, if you have a link to the longer talk, if it's being pre-recorded, we could put that in the chat messages, and that will also give a nice pointer to people who can see the full version, because we can make sure all the attendees see that too.
Yeah, everything is at my website, and if one goes at my website, which they should have no difficulty, there's a link to the new book and also to my earlier book on reinforcement learning, and everything is very clearly given there, all the papers, including and the YouTube 1-hour talk.
That's wonderful. Do you mind stopping sharing your screen, please, so that Nathan can set up his?
Share my screen. I thought it was sharing.
Oh, no. Can you stop sharing your screen? Because that way the next person can start to set up. So from one MIT connection to another, we're next going to be having Nathan Kallus, who did his PhD at MIT, give a talk. Nathan is now an assistant professor over at Cornell Tech, who spans a number of different really interesting research areas. He's won multiple awards, including an NSF Career Award. And we're excited to hear what he has to say today about statistical efficiency in offline RL, which might also connect to what Peng was talking about earlier today. Thanks.
It will. Thanks, Emma. Thanks for the introduction, and thanks to all the organizers for organizing and inviting me. It's a pleasure to be here. So I'll be talking about a series of papers that are joint with my student Masa on the theme of statistical efficiency in offline RL. And the motivation for the work is largely the potential for using reinforcement learning in medical applications. So one example of that may be sepsis, which is when the body has an extreme reaction to an infection, and the organs start shutting down. And it's a leading cause of death worldwide, but despite having this very morbid status, it's really not clear what's the best way to manage sepsis and to treat patients in a dynamic way, largely because there's a lot of different interventions that a doctor can take. They can apply vasopressors, give IV fluids, take away IV fluids, and there's potentially a lot of heterogeneity in how that might impact different patients and their very subtle symptoms. So maybe this is a great opportunity for reinforcement learning. Maybe too many patterns for humans to process, but maybe a machine can do well here. Of course, in such high stakes domains, exploration is going to be very limited. We can't just go out and apply vasopressors or take them away just to see what happens. And we have to take care with every action that we take. So in these settings, we really have to rely on existing data like EHRs as has been mentioned this week in this excellent workshop. The important thing is, so there's a lot of this data out there, but we have to take care to use it correctly. So one example of doing offline RL in medicine is this Nature Medicine paper that proposed the algorithm they call the AI clinician, where they took EHR data, electronic health records, from an ICU. So this was observational data. They used a MIMIC data set, and they applied RL to it specifically to train an algorithm to treat sepsis. But this was actually met with quite a bit of scrutiny and skepticism from both the reinforcement learning and medical communities. And there's a lot of discussion there. But in my summary, I think one of the biggest gripes was essentially that a lot of this was highly unreliable due to what's known as the curse of horizon. So what Komorowski et al. Did to evaluate how the algorithm was doing was importance sampling and rejection and importance sampling. So it would go something like this. Each patient in their data set, they would see what their algorithm did. For example, in the beginning, did it apply mechanical ventilation or not? And if it agreed with the observation, they kept the observation. If it didn't, they threw it away. They did the same later on down the line. Did we apply sedation? Our algorithm would apply sedation. Did the data set, did the day points have sedation at this point? No, throw it away, and so on and so forth. And the immediate thing to see is that as the horizon grows, as there's more opportunities to think about actions that we would take versus what happened in the data, the amount of data is going to whittle down into absolutely nothing in a geometric way. So the aim of the talk that I'm going to give today is to try to think about, well, how can we overcome these fundamental limits by leveraging problem structure? In particular, Markovian structure or time invariant structure or ergodic structure. And essentially the theme of how I'm going to tackle this is, we only have the data that we have in offline reinforcement learning. We can't go out and collect more. That is the definition of the problem. So we better use it to its mostest. We better use it efficiently. But actually, if you think about what efficient means, well, that's going to depend on the problem structure. And as we change the structure, what efficient is changes, and we can actually see at what point do we get past these limitations. At what point is the lower bound better than what we want? And at what point is the lower bound telling us that everything is hopeless? So what I'm going to do is, what we've done in these series of papers is study the efficiency limits in a variety of offline reinforcement learning tasks in the MDP model for the first time. And this gave us insight into when the curse of horizon bites, because we can see what the limit is. And if the limit is too high, then there's no hope. And this really paints this as a problem-dependent phenomenon. It depends on the problem and what you assume about it, not an estimated dependent phenomenon. It's just a question of achieving this bound. So after studying these limits, I'm also going to provide the first efficient estimators for both policy value and policy gradient estimation from off-policy data in the MDP model in both finite and infinite horizon settings. And there was a little mention about Donsker and entropy conditions earlier. So these actually will remain efficient even when we are going to estimate deducences at slow rates using black box machine learning, making no entropy assumptions on them. So in outline of the talk, unfortunately, I think since I started late, I'm going to eat it into the break, but I'll try to minimize that. And so I'll start by setting up the problem and defining some of my notation and describing what efficient means. And efficiency here will be kind of the instance-specific bounds that Martin mentioned on the first day when he was talking about Lecam's theory, and it's related to what Peng was talking about. And then I'll present our results on the efficiency bounds and how these limits change as we change the structure. And then I'll talk about how we can actually achieve these bounds using an algorithm that I'm called double reinforcement learning, which is a riff on the double machine learning name. And then I'll talk first about that in the context of off-policy evaluation. Then I'll switch gears to talk a little bit about off-policy gradient estimation, because there's some interesting, unique things that happen there. And we can talk also about implications for policy learning in that case. And then if there's time, I'll also talk about some experimental results. So the working model for reinforcement learning is the Markov decision process, the MDP. I certainly don't need to define this for this audience, but it'll use the opportunity to tell you about my notation so we're all on the same page. So we're going to have an agent, for example, the doctor, observe the state of the environment here being, for example, the patient. And based on this state, she's going to act according to some policies. The policy is simply going to be a distribution over actions given current state. And in reaction to this action, the state is going to advance, so the environment is going to advance to a new state, which is described by this transition probability, which depends on the current state and the action we took in it. And it's also going to emit a reward that depends on the current state and the action that we took in it. And if you think about it, if you take the MDP part, right, what's the problem? The problem is defined by the state and reward probabilities that defines the environment. And you combine it with a policy. What are we going to do in every state? How is the agent acting? Then if these are just two different sets of probabilities, if you multiply them together, essentially what this induces is a joint distribution over the random variables given by state, action, reward, state, action, reward, state, action, reward. Okay, so we have these random variables, and this is going to give us a joint distribution over them, and they're going to satisfy this this essentially causal DAG encoding the independencies encoded by the Markov assumptions. And what we want is just to maximize reward. So we're going to look at the average reward over time. So average from t equals 0 to t of the reward that we see. And we can weight it by a discount factor gamma. And we can also look at the long run average reward, which is when we take t going to infinity. So OPE is just a task of, if we're given a policy pi that we care about, we want to estimate its reward. But the data that we get is n observations of t long trajectories from playing the MDP with a different policy, pi b. And the behavior policy may be known or unknown. I'll focus on known, but actually the efficiency results don't change whether it's unknown. The key difficulty here is that the estimand, the thing we want to estimate, is an expectation under one probability distribution, but the data is coming from a different probability distribution, so we can't just take sample averages. That's for evaluation. What about learning? Well, then, in this case, we suppose we're given a parameterized policy class, parameterized by this policy parameter theta, and we're going to simplify the notation and simply say value at theta is the value of pi theta. And then the off-policy gradient is the problem of estimating the gradient of the policy value given n observations of t-long trajectories from a different policy. Now, we can use this common trick of rewriting the policy gradient in terms of the policy score, which is the gradient of the log of the policy. And we can rewrite the gradient again as just an expectation. So now we don't have to, this gradient operator is built into the policy score, which is just a function of our policy. Again, the difficulty is this is expectation about with respect to one distribution, the data is coming from a different distribution. Why care about policy gradients? Policy gradient methods have driven a lot of the successes recently in reinforcement learning, whether it's playing video games or moving a robotic hand to solve the Rubik's cubes. That's of course in the setting where we can explore and simulate, but hopefully that is will tell us that maybe here there's also potential for policy gradient methods. So a very, very, very brief overview of some existing approaches to these problems. And this is kind of a very minimal overview. I don't mean to detract or minimize any of the things I'm not mentioning. I'm just trying to give a flavor of some of these things to be self-contained to some amount. So maybe the simplest thing you could do for OPE is the sequential importance sampling estimator, which is simply the following. We're going to take the cumulative density ratio, which is the product of the ratio between the target policy and the behavior policy. The behavior policy is, of course, the one that's generating the data. And what this lambda t does is essentially just change measures from the distribution under pi b to the distribution under the target policy. So then we can construct an estimator simply given by taking the empirical expectations. When I say E sub n, I mean 1 over n sum over I of this quantity where each thing here is going to be applied to the ith data point. And because the data is coming from pi b, this expectation is going to look asymptotically like a population expectation with respect to p pi b. But we put these lambdas here so that we're actually changing to the target distribution we want. So that's what important sampling does. We can add a control variable to this, and this leads to what's known as the W robust estimator. And the reason I'm putting it in quotes because there's a lot of things that are W robust. We're going to talk about other things that are W robust. But in the context of OPE, this particular estimator has been dubbed the doubly robust estimator. So that's why I'm calling that the DR estimator. And here we just take the SAS estimator and we add a control variable. One example of a control variable is the Q function. So the Q function is the expected rewards to go if we're following the target policy and we're currently in state ST and we're going to take action AT. You can either think about it as a function of STAT or as a random variable that's measurable with respect to the random variables STAT. Here we estimate Q hat T and plug it in. Of course, if we're in the infinite horizon setting, Q is independent of T. And there's a lot of variants of this, which are essentially looking at different ways of choosing the control variable rather than plug-in ways, maybe some optimal ways or some shrinking ways. And there's different benefits to these, but I won't have time to talk about that aspect of the problem. And then for off-policy gradients, there is methods that are, again, doing importance sampling. Just take the expectation to define the policy gradient, add lambdas, change it to empirical expectation. This is sometimes called reinforce. There's also a way to rewrite it using Q functions. This leads to an estimator called off-pack. And a super naive view of the cursive horizon, we're going to be a bit more technical later, is that even if the policy, the target policy is such that the ratio between the target policy and the behavior policy is roughly constant, so it's in some sense bounded, right? If these are the same policy, this will be one. If there are different policies, this will be sometimes smaller than one, sometimes bigger than one. So I mean, like a moment is roughly C. Then we'll have that these lambdas are going to grow exponentially. All of these estimators have lambda in them, so they will all have variances exposed exponentially, and we'll have infinite variance in the infinite horizon setting. Quick mention of some other things we could do. We could just do the direct method using Q. Then we can just bake in the MTP structure into the Q model. There's also methods recently looking at different kinds of importance sampling using stationary or marginalized density ratios. And these leverage MTP structure, which is great and makes a dent in this problem, and it motivates our current study. You know, definitely want to give credit where credit is due, but these are still not efficient. In general, that means they will have a suboptimal leading constant in their variance. But more generally, these will actually, in non-tabular, non-parametric settings, this will actually generally have a slow rate because these estimates that we're going to need to estimate, like Q, we won't be able to get parametric rates there. So this bad rate will then influence the rate of these. So what do we mean when we say efficiency? What are we going to try and get to? So again, very abridged description of what this means, just enough to tell you about our results. So efficiency goes like this. We suppose we have a model, which is simply just a set of distributions for the data. That's what a model is, okay? We have a parameter of interest, which is just some aspect of the data generating distribution, some function of it. Then we fix the data generating distribution, which is an object of the model. And the data that we see is IID observations from it. What we want is we want a good estimator, which is a function of the data, for this true parameter, which is a function of P. And of course, we want to use the data to the mostest. One of the big punchlines of semi-parametric efficiency theory says that any estimator is going to work for all instances in the model, okay, or technically is a regular estimator. If it's going to work for all estimators, then for if it's going to work for all instances, then for each specific instance, it also has to satisfy this lower bound, where if we look at the mean squared error of the estimate, we scale it up by n, the limit infimum is going to be lower bounded by this quantity called the efficiency bound, which is given by the 2 norm of what's known as the efficient influence function, which is the least norm derivative of tau when we take derivatives with respect to the DGP in the model. And actually, I just want to correct something that Peng said. Peng was actually, when he gave the definition for a regular estimate, he actually gave the definition for asymptotically linear, which is different. And the difference is actually really important between regular and asymptotically linear, because asymptotically linear is an instance-specific property, and regular is a model-dependent property. And efficiency depends on the model, because in some sense, you want an estimator that works for all things near the instance in the model. So those things are actually different, and they only coincide in the case of an efficient estimator, but it's important to distinguish between them if you're going to define what efficiency means. So how do we apply this to our problem?
Can I just interrupt you for a second? Could you just go to the chat and answer a couple questions from Robbie? about the change of measure.
Yeah, can you tell me about the questions, or should I?
Yeah, so Robbie's asking about there should be at the bottom of the Zoom a Q&A, but if you can't, I'm happy to do it. So Robbie was
Yeah.
asking in terms of the change of measure, like a radon nicodym derivative,
Yes, exactly.
in terms of the non-parametric Tispakov. I said that wrong. Might need
So
to
what is the question? The question, does this requires an absolute continuity between the target policy and the behavior policy? That's correct.
All right, thanks. Robbie,
Was that the question?
I believe so, but it's
Okay.
not. So Robbie, I'll promote you to being so that you can ask additional chat messages or jump in live if you'd like to. So let's keep going, and then we'll jump in with additional questions.
Okay, thank you. So how do we apply this definition of efficiency to our problem? Well, for us, the target estimate is going to be the policy value or the policy gradient. And what's the model? Well, the model is the DGP. Where's our data coming from? Our data is coming from trajectories from the behavior policy. That's P pi B. So the model is the set of all such distributions when we vary the MDP problem. Okay, so if pi b is known, then that's going to stay fixed, and we're going to vary the MDP arbitrarily. And essentially, to be regular would mean to work for the MDP model. But it's actually going to be quite insightful to look at other models that are larger than the MDP model, corresponding to larger efficiency bounds, in order to understand what are we gaining. So in particular, we're going to consider 3 nested models. So the Markov decision process model is at the bottom, is the one I described so far. We can actually make the transition, reward, and action probabilities time dependent. So that's going to lead to something we call the time varying MDP or TMDP model. We can also let the transitions, reward, and actions depend on the whole history of taken actions. In a sense, we're dropping the Markovian assumption, so I'm going to call it the non-Markov decision process, or NMDP, right? So if we make a line here at S1, the bottom 2 models decompose, but the top one does not. So what happens in these different models? So to avoid having to define a lot of different notation for different importance sampling ratios, etc., I'm just going to give you the punchline of the efficiency bounds results that we have. And just to kind of drive things to the hardest limit, I'm going to look at the infinite horizon of policy evaluation or of policy gradient problems. The rates here I'm going to show are the same. So the setting is we've observed n trajectories of length t from pi b, and we want to estimate the long run infinite horizon reward for a given target policy. So first, in the NMDP, what you can show is that if these density ratios are sufficiently big, so they should be bigger than 1 over gamma. In particular, if they have just this log moment that's bigger than 1 over the gamma, then the efficiency bound under the NMDP model is just infinity. There's just no way you can beat this, okay? So this means we must suffer from the cursive horizon. There's no way around this. Any estimator that works in the NMDP model, including the existing estimators I talked about in the beginning, must suffer from this. On the other hand, if this cumulative density ratio actually is not growing exponentially in gamma, then you can get a finite efficiency bound, and the MSC will scale something like 1 over n, 1 over the number of trajectories. Okay, but essentially this is like saying that these ratios are bounded by 1 over gamma. So if gamma is 0.9, it means bounded by like 1.1, which is essentially like saying you're in the on policy setting. So that's why I put a little video game character on this. It's essentially like on policy evaluation. What happens if we impose the Markovian structure? If we impose the Markovian structure, we can still have this finite efficiency bound and efficient MSC scaling like 1 over n. If instead the cumulative density ratio, just its marginalization with respect to ST and AT, is not growing too fast. And this is a much more lax condition. In fact, you can show that this condition must hold, and actually this is going to be big O of 1 if we're in a setting where the transition and reward and the action probabilities are all time independent. Then you necessarily will have this is kind of bounded by 1. But if you're going to assume that, then you're assuming the MDP model, but you're using the TMDP efficiency bound. So this is essentially just a crappy bound for the assumptions that you're making. If you're going to assume MDP, you should ask to be efficient in the MDP model. So what's efficient in the MDP model is actually not just a lower constant here in front, but it's actually a different rate altogether. In the MDP model, every transition, every state action reward state observation is informative. So really the scaling should be 1 over n times t, which is the number of observations that we see. And you should be able to get this even if you have just a single trajectory of growing length, as long as you're assuming some ergodicity about this single trajectory.
Hey, sorry. Could you explain a little bit about the ergodicity assumption? Like, yeah, I have a background in math.
Yeah. So essentially, yeah.
Like,
so we want to assume that we'll need to assume that the Markov chain induced on state action reward by either the evaluation or behavior policies, it has to be Harris ergodic. And of course, there's also the assumption that these rho t's exist and have an L2 moment, which is kind of an assumption in here as well.
oh, this is sort of a existing assumption. You haven't changed that part of the assumption.
Right. I glossed over it, right? I think that was the question. I don't know if this is the same person who asked the question before, right? But by assuming these exist, this is assuming the Verdon-Nikodym derivative exists, which is saying they're absolutely continuous. But also this is going to be MSC, so they also have to have an L2 moment. They have to be an L2 variable.
L2 moment for which moment of the gradient?
No, rho t.
Oh, rho. Okay, sorry, thank you.
Yeah.
I think we might need to just give him time. I want to make sure Nathan has a few more minutes to go through the rest of his talk. So why don't we hold additional questions on the technical details, which are very important, but let's just postpone those to the end.
And I'll be connected during the break. I'm happy to stay on and chat with anybody who's interested to ask more questions. Okay, so I put this money face emoji here because this looks great. We want to cash in on this awesome rate. How do we do that? Okay. So for that, I'm going to present, first I'm going to focus on the case of OPE, and I'm going to present the double reinforcement learning algorithm. Before I delve into a specific instance of it, right, where there's a lot of cases that we consider in these papers, so just to give an overview of what's the nature of the results. So here's essentially what we do for each of these cases. So for each of the cases being whether we're looking at MDP, TMDP, NMDP, whether we're looking at the off-policy valuation, off-policy gradient problem, whether we're looking at finite or infinite horizon, what we do is we derive the efficient influence function for each one of them, right? And that's the least norm gradient of the estimand, which plays the crucial role in the efficiency bound. And all of these EAFs are going to involve some nuisances. So in particular, they're all going to look like some function phi, which is going to have expectation tau minus tau. And phi depends on some nuisances something that depends on the DGP script P. So the nuisances actually change by case, but one thing that is an example in all of these cases is the Q function. In all these cases, one of the nuisances is going to be the Q function. So if we did know the nuisances, we could just take a simple average of this phi, and that will by definition be an efficient estimator. But of course, we don't know it. So one idea is estimate these things, like estimate the Q function, plug it in, take empirical expectations. So that kind of works. We have to make sure it works, and we have to kind of tweak this. So first, for this to hopefully even work, we have to prove some properties about the efficient influence functions. So we prove that they satisfy a certain double robustness property. So in the case of OPE, there's going to be two nuisances. So I'm going to call them eta 1, eta 2 generically. One of them is Q. And actually, if you just plug in the correct eta 1, but anything for eta 2, or the correct eta 2 and anything for eta 1, they will still be unbiased for tau. Okay? And there's a slightly different, interesting case for OPG. Hopefully, I'll get to talk about it. So this essentially shows that taking empirical expectations of phi is really insensitive to errors in eta hat as long as it's sufficient close to eta. This is something known as Niemann orthogonality. So then to leverage this, what we can do is we could use cross-fold fitting to estimate these eta hats. So I'll explain this in a specific example in the next slide. And this is a technique that's been coined as double machine learning in a recent paper by Chernyshchukov et al. And what this does is allows us to use very flexible machine learning estimators without making any conditions on these estimators. Okay, and again, there's going to be some interesting special case that differentiates from how cross-fold fitting is done in double ML due to the problem that we have one long trajectory with dependent data. So let me give you an example. So let's look at infinite horizon OPE in an MDP model. If you had many trajectories, you could just use two folds. But let's look at the one trajectory case, because it's kind of interesting. Suppose we have a single trajectory of length t, and t is growing here. So we're getting more and more data because this trajectory is growing. So what we do is we're going to split it into 4 folds. Okay, D0, D1, D3, D2. So I kind of numbered it a little bit funny. You'll see in a second why I numbered it this way. Then what we're going to do is first, let's define W to be the ratio between two things. One is the gamma discounted average visitation distribution under the target policy, divided by the undiscounted stationary distribution under the behavior policy. So this is slightly different from Liu et al., where they actually use the same kind of discounting. But actually, the thing that comes out from the efficiency analysis is this ratio, because the data that we see is not discounted, but the evaluation we want to do is with respect to a discounted distribution. So then what we're going to do, we're going to look at each one of these 4 folds. And in each one, using just data inside that fold, we're going to construct estimators for this W and for the Q function, using only data in here. And I put a star here because I didn't really tell you how to construct these estimators yet, but use some black box magic, use only the data here, construct an estimator. And then we're going to set our estimator to be the average, the time average over the trajectory of this function phi, which is coming from the efficiency analysis, which depends on state, action, rewards, state, next state. So we're going to feed it all of the transitions that we observe, and it depends on W and Q. So when we're looking at a transition in, let's say, D3, we're going to use the nuisances estimated on D0. When averaging on a transition inside D1, we're going to use a nuisance from D2. And the crucial thing here is we want the transition to look independent from the data that we use to fit these nuisances. And the reason we split into 4 when we have a dependent trajectory is that as this trajectory grows, under sufficient ergodicity, we're going to have that, for example, this D3 segment is going to grow, so D1 is going to be farther from D2, so they're going to look more and more independent. In particular, we can show that if we assume certain ergodicity conditions, and if each one of these nuisances is fit at a rate alpha 1 for Q, alpha 2 for W, then if these alphas sum to at least a half, and we have some mixing conditions on the data, then our estimator is going to be asymptotically normal and efficient. It's an asymptotic variance will be controlled by the efficiency value. And the key feature of such a result is that we're making no assumptions of these nuisance estimator, just a slow rate. Okay, so we don't need to impose Donskoy conditions. If we didn't use cross-fold fitting, we can still do this by imposing Donskoy conditions. And the rates can, for example, be slower than parametric, that is 1/2 rates. It could be a quarter or anything that satisfies this trade-off over here.
And Nathan, I'm sorry, we'll need you to wrap in about a minute. If you
Okay, so I'll just skip the OPG section. I'll finish this and I'll conclude. Thanks, Emma. So we can also show a certain double robustness guarantee that just it's enough for one of these estimates to be consistent for the estimator to be consistent. So essentially, if each one of these circles represents where one of these models is consistent, then we're consistent anywhere in this union, and we're efficient when both are consistently estimated at slow rates. And some example cases of this. So for example, if you're in the tabular setting in MDP or TMDP, that is if the state and action spaces are finite, we can obtain parametric rates for all the nuisances because they're all essentially parametric, and then we get efficiency. We don't even need to use cross-fold fitting. In a finite state space with a known behavior policy in a TMDP, this paper Xi et al. Actually provides parametric rates for the marginalized density ratio. So we only need to get consistency for the Q estimate, absolutely no rate. So just using kernel regression estimates here will suffice here as long as Q is bounded, which is enough to just assume rewards are bounded in order to get boundedness. So again, you immediately get efficiency. Right, the game here is once you have this meta estimator, how do we get the nuisances to satisfy the conditions? In the general non-parametric case, you could use general flexible machine learning estimates. You would just need to get something with a rate. We're making no further restrictions on them, such as Donskoy or other entropy conditions. So for example, you can use dual dice or the other dice papers to estimate W. More generally than that, W and Q are both just quantities that are defined by conditional moment restrictions. So you can use some classic theory on solving non-parametric conditional moment restrictions, or a recent proposal that I was involved in of actually solving these with neural nets using adversarial training. So these can, for example, help you get more machine learning neural net estimates for W and Q. And there's a variety of other results in the paper about efficiency in the other models, finite sample guarantees, inefficiency of other estimators, etc. And unfortunately, I won't be able to tell you too much about off-policy gradients, and I'll skip the experimental results, and I'll just kind of summarize about what was the point of this. Well, we wanted to overcome these fundamental limits in offline reinforcement learning. And the key was to leverage problem structure, because if we don't assume anything, we got nothing. And we're going to be hit by the curse of horizon no matter what we do. It's not an estimated dependent thing, it's problem dependent. In order to get past this, we have to impose structure. So we studied the efficiency limits in off-policy evaluation and off-policy gradient estimation for the first time in the MDP model, and we provided the first efficient estimators for this. So that's it. I'll end here. Thanks.
Thanks for the great talk, and I am sorry that there was. It would always be great to hear more from all of the speakers. I'll let everyone go to the break in just a second, but I'll first see if there are any questions people wanted to raise immediately. So one person did ask, the idea is to split the data to make them independent, correct? What is the property of the data in one group? I'm assuming it's just a random split, but I'll let you comment.
So it's not a random split. It has to be according to the time index, because we want D2 to look independent of D1. Because this D3 is going to grow, make these two segments of the trajectory separated. So essentially, think about that picture I had before about SAR, SAR, SAR. This is essentially what these little boxes are boxing in. So it's boxing in those transitions. In the case where you have more than one trajectory, like even if you had just two trajectories, it's enough to just split it into two folds. You just need to make sure that you're independent. And notice that you don't get a deterioration in the rate, that it's like n over 2, or sorry, in the constant. You don't get like the 2 in the constant, because you're still averaging over all folds. Every fold plays both roles of nuisance estimation and a transition that we average over.
Yeah, I was thinking about the episodic case where you'd split randomly on the transitions, where that would be sufficient, but yes, for a long trajectory.
Yeah, you have to make sure you got the independence, yeah.
And I guess one other quick question I'll ask before we break is, I think that the theoretical results here are really exciting, and it's great, sort of the generic types of nuisance parameters. What's your sense of whether or not this will lead to sort of impact on empirical estimates? I know we didn't give you a chance to talk about those, so either that would be a chance to flash up a slide, or to talk more generally of whether or not you think these insights will lead to sort of more efficient and therefore like more accurate mean squared error estimates.
Absolutely. So, in some sense, what I shoved under the rug in this is the nuisance estimation, right? I just said, if you have sufficiently fast nuisance estimators. But I think in practice, I would still opt for something orthogonalized like this, even if they weren't consistent, even if I was using, I think it was you, Emma, you mentioned this example of, well, who knows if a 2-layer neural net is well specified. So theoretically, of course, you could grow the neural net deeper and wider, and that actually can achieve minimax rates. That's kind of like this result by Sanjog Misra, Max Farrell, and the third author who, very embarrassingly not remembering their name. They give kind of, what are the rates that you get for doing this? And it's some sort of assumption about how much smoothness you have. But again, that's purely theoretical. When you're going and applying this to sepsis, who knows what the smoothness is? But I think this is still giving us insight and telling us, well, you should not just do direct modeling. You should not just do importance sampling. That will be extremely sensitive to whatever it is that you devise, whether it's a 2-layer neural network or something much more complex, like a very deep neural net. You should combine these things in order to be orthogonal to this error. That's essentially what this property tells us. We want to be insensitive to errors in eta hat, even if we can't guarantee these rates to prove these theorems. So I definitely think this is kind of it's a meta algorithm, and to get some results about efficiency, you have to invoke smoothness and to show certain rates. But I also think it's a recipe for applying this in practice, where you should aim for insensitivity to errors in your nuisance estimates.
If I can ask one question about you're talking about smoothness, like so does it I didn't understand if you meant that it required smoothness, like you want it to be you want your data, you want somehow you are actually actively smoothing, like you're convolving with
No.
Gaussians, or you're actually you're actually saying you should be resistant to smoothness so that you should get as low regularity as possible, like maybe even like
Yeah.
non-differentiable, like crazy regularity.
Yeah. So
just maybe just to interrupt before, just to say, let's absolutely continue the discussions on this. Just as a quick reminder for people that might have to pop off, grab coffee and come back. A reminder that we'll be starting again in about 10 minutes with the next speaker. And so Nathan, thank you so much, and Ravi, go ahead.
Yeah, so there is no smoothing here, right? The estimator is just this thing.